probably should have prefaced this. I should have told you. So these are the tax graphs, but these questions, as you see, are kind of general for any focal quantity. So I hope you didn't focus too much on taxes when you were answering these. You shouldn't have. Okay, you shouldn't have. But if you did, it's okay. So first question. So in general, we got a graph for the accumulated amount and rate of change. Which is which? Which is accumulated amount? Right. Rate of change on the left. Okay. So more specifically, these graphs show how two quantities change together, covariation. So let's talk about those two quantities. First quantity, input, the independent quantity. How and where in the graphs is the measure represented? Which x-axis? Both. Both, okay? It's the same quantity on both graphs. That's the input. This is independent quantity. Okay, output. Where do we see this? The output quantity or y-axis? Both graphs? Only the right graph will be the output, okay? So here's a crucial question now. Which quantity, input or output, measures the accumulated amount that's central? So is it the input x quantity or the output y quantity when we talk about the accumulated amount? That's the y. That's what we're talking about. We're accumulating whatever this y is. This is our kind of focal quantity in the situation. Okay? Okay, so now delta y equals k delta x has everything to do with this. It's everything to do with this. So let's talk about how that fits in. Okay, what does k represent in general? What is it? Rate of change. Okay, rate of change. And where do we see k in these graphs? Vertical axis on the left-hand side, left-hand graph. Okay, that's k. That's where we see k. Okay, so how could a value of delta x be represented? And I said there was the same delta x you could show in three different places. So here's an example. So this is kind of open-ended, but here's an example. Okay, delta x there, same delta x there, but could also be shown up here. Okay, so that's the same delta x being represented three different ways. It's looking like I'm going from what 40,000 to 50,000 as my delta x. Here we go. So what about delta y? What about the delta y corresponding to this delta x? Okay, right there. Now I didn't show the other place where you might see it, but you could transfer that over here. You could show that delta y on your y-axis over here. Okay. All right, so how is this delta y calculated? How is this delta y calculated? K delta x, right, K delta x. Okay, so which value, from what value of delta x? From what value of delta x? Well, obviously that one right there, okay, which is that one right there. And then what about the k? Which value of k is going to get us, are we going to look for in calculating that delta y? So can you track it? Can you map it out? Which value of k would it be? Yeah. Right, so it's going to be the one that corresponds to this delta x up there. That's going to be the k, right? That's going to be the k that you're going to use, and that'll be the delta x that you use to get that little change in y. Okay, so we're going to revisit this. So like the top hat will be like the first half of the questions, like the first, what is it? First six. First six will be top hat, okay? On Wednesday, first six. Okay? And then we will revisit this slide maybe once a week because this is everything. So you've got to have this orientation of what the quantities mean, where they go, what you're looking at, or else you'll be lost, okay? You'll be lost. Okay, so let's return to specifically the tax example, and we're looking here at a current value of what? What's the current value of income right now? 58,000. About 58,000 is the current value of income. And so the question is, how can we symbolically represent the tax due on 58,000? Two different ways. So we thought this is where we finished off last time. We could represent this tax due on 58,000 as a total amount of tax and as the accumulation of small amounts of tax for each dollar earned. Okay, so how could we represent it as a total amount of tax? How could we represent the tax due on 58,000 as a total amount of tax? What's that? Right, so we would just take that 58,000 and we put it into which function? The left function or the right function? Right, okay, so we put the right function. Okay, what about the other way? So here I showed you. So the accumulation of small amounts of tax. So what I'm showing is here the change in tax for the first dollar earned plus the change in tax for the second dollar earned. Okay, all the way up to the change in tax for that last dollar earned of 58,000. So how many things are we adding together here? 58,000 little bits of tax. 58,000 little bits of tax that we're adding together. So you think about, Sarah makes her first a little bit of income on day one. She makes that first dollar, and she owes some tax on that. She owes some tax on that. Then she makes her next dollar. She owes some tax on that. So you can think about this tax due as the accumulation of little bits of tax starting January 1st up until that moment when she's earned 58,000. Okay, well, so what's our focal quantity here? Our focal quantity is tax due. It's our Y value quantity on the right-hand graph. And so we could also think of those little bits of tax as little changes in Y, right? Little change Y1, little change Y2, little change all the way up to the little change of Y for the $58,000 earned. Okay? So, but this, really we keep writing the same thing over and over again, right? We keep writing delta Y, delta Y. So what we do is we write it once, and then we have a symbol that just means we're going to sum these over and over and over again. Okay, and so that's this Greek sigma, standing for sum. So all that means is we're going to sum up a bunch of these. They all look the same. But there is something different, right? That these amounts of tax, we have these subscripts who are telling us the first amount of tax, the second amount. So that's the one thing that changes. So we use what's called an index. And that I, so that I is going to change now. That I is going to be 1, and then it's going to be 2, and then it's going to be 3, etc., all the way to 58,000. And each time it changes, we get another delta Y that we add on. So that's what that's signifying. So we need to signify what I starts at. What is I starting at? So we do that on the bottom of the sigma. We say I starts at 1. And then at the top of the sigma, we say, what's the last value of I? 58,000. So this right here, all that notation right there has the exact same meaning as the red line right above it. Okay, so how do we say that? It's the sum of delta Y sub I as I goes from 1 to 58,000. It's the sum of delta Y sub I as I goes from 1 to 58,000. So those are absolutely equivalent. It's just, this is a lot more convenient that rather than writing out delta Y over and over again. This is a shorthand way to do it, okay? So let's practice a little bit of that. So see if you can, let's just do this together. So if we wanted to add the numbers 1 through 100 together, how could we use summation notation to do that? How could we use summation notation to do that? It's going to be a sum. Okay? And so let's talk about our I will go from what to what? 1 to 100. And then what is it that we keep summing over and over together? Just going to be I. Because we want the first term to be 1, and then we want the next term to be 2, and then 3, and we're going to add all those up, stop at 100. Yeah?
So is I your starting value of what you increment by?
No. It's I is called the index. It's like it's like a variable. It's taking on all these different values as you go through the sum. So below the sum, it's just you signify what the starting value of I is.
And then, but how do you know how much to increment by?
Oh yeah. So I will always go by ones. It will always go by ones. So we could have started here at 3, but it still would have gone 3, 4, 5, 6, 7. Good question. So the increment always goes by ones. You always go by ones in these. Okay. So it's like the first term, the second term, the third term, the fourth term. Okay, so I want you to write out, like this is the opposite now. I'm giving you the summation notation, so I want you to practice writing out as a sum, what would this be like as a sum? So let's see if you can do that. So if you were to write this out the long way, what would it equal to? Go ahead. Is this what you put? This is what it is. So those two things mean exactly the same thing. They mean square 1, and then add it to 2 squared, then add it to 3 squared, add it to 4 squared, 9 squared. So when you just come and you look at this, you get some sigma notation right in front of you, okay? You need to see, so you're going to be given off and you'll be given what you see on the left. You have to think what's on the right. So if you need to write it out, write it out. But if you're given something like that on the left, then your brain has to be like, oh, I know exactly what that means, what that thing is on the right. Okay? Okay, try this. See how this goes. So this is I equals 1 to n. This is an n. R sub I delta x. Okay, try that. What does that mean? So n then is unknown. Could be a different value. Here's what it would be. Okay, you try and write that in summation notation. You try and write that in summation notation. Okay, this is what it would be. Sorry about the blur. Okay, all right. Deep breath. You don't have to use I, but I is fine. You can use something else. Okay, so it's not about right and wrong. It's not about right and wrong. You can use something else. So here's an example of using something else. If you put I equals 1 to K, and then you had an I there, it's the same thing. Okay, so if you had I there, and I there, it's the same. but J is often used as well. Okay. What do you notice about this? What do you notice about these terms here in this example? Yeah.
It could be like the rate achieved,
Yeah. Right. This should look familiar, right? Rate times what? What is that equal to? It's a delta y. That's a delta y. So this could, you could think of this as delta y1, delta y2, delta yn. Okay, so there's some familiarity to that particular sum right there, summing up these little changes in y, but written as k delta x, k delta x, k delta x, k delta x. Okay, so we're going to change up the example here. So let's think about a rocket-powered basketball.
No way.
Yeah, way. Okay. So what's happening here? So we have, these are our two graphs. All right, so flip over your white sheet. Flip over your white sheet. And I got some questions on the rocket-powered basketball. Okay, here we go. So what is the input quantity in this situation? Okay, so time since launch. Okay, time elapsed since launch in seconds. And where can we see that value increasing? Yeah, so it'd be the x-axis. I'm not actually showing it here, but it could be shown on both, right? It could be shown on both. We're just showing it increasing on the left graph in this particular example, okay? But it's the same exact, that is that same quantity here on this x-axis over here. Okay, question 2. What is the rate of change quantity in this situation? So what is the meaning of the rate of change in this case? Second, which would be like, what is that? Speed, right? So speed. So the rate of change in this case, we're talking about speed. Feet per second. And where do we see that? Y-axis of the left graph is our rate of change, right? Speed, okay? All right, what's the output quantity, i.e. the focal value that's accumulating? What is the focal value that's accumulating? Okay, feet from the ground, which is a measure of height, right? Height, feet from the ground, height. And where do you look to see its current value, or its value for the current value of elapsed time? Y-axis of the right graph. Okay. So I've stopped here at a point. What does that point, that blue point on the left-hand graph represent? It represents a rate of change. Does it represent a rate of change?
Yes. At a certain time.
At a certain time. It's two values, two corresponding values taken together. So let's estimate what it is here. This particular point is 5.2 maybe. Two values taken together. And what does it look like here? 10, speed is 10. 10 feet per second after 5.2 seconds after launch. Okay? So, why does the graph of the basketball speed versus elapsed time jump discontinuously? Well, that's a good question. The reason is because it has booster rockets on it. And every half second, another booster rocket goes off, and what happens to its speed?
It increases.
Jump. How does it increase? Gradually?
It's not it's insane.
Jumps suddenly. Okay, so the rate jumps. It's going at a constant rate, and then all of a sudden, you imagine that the booster rocket goes off, and it's suddenly at a higher rate for the next half second. So every half second, the speed of the basketball suddenly jumps to a higher speed. Okay. There actually were bombs in World War II called buzz bombs that kind of had this effect. Okay, this is very theoretical and impossible. Okay, but there were bombs that were something like this. They would go, and then a rocket would boost off, and then it would suddenly be traveling faster. Okay. Okay, so big ending question here. So, in what way does the basketball heights accumulate? So, This idea of accumulation is where we're going to be our focus in the next month or so, or 2 or 3 weeks. Okay? What is this thing accumulation? What is it about? How do things accumulate? How do quantities accumulate? Okay? So you can see here, over here, the height, every half second, these red dots are showing the new value of height. So in every half second, we get a little bit of height added to the previous total height. And that's the idea of accumulation, that quantities accumulate bit by bit by bit. So delta H1 plus delta H2 plus delta H3. And these are just like delta Y's, okay? So these are delta Y's. So any quantity whose value is changing can be thought of as changing in bits. A little change plus a little change plus a little change plus a little change. That's a big theme here, okay? So that's how the height can be thought of as a first little change in height in the first half second. Then a little change in height in the second half second, etc. Change in height. Bit by bit.